Hey everyone, welcome to this explainer. Today, we're skipping the fluff and jumping straight into the thick of things. We are going to unravel a really fascinating real-world engineering dilemma that's basically the heartbeat of embedded systems and programming.
So, picture this. You're building a robot. And I'm not talking about a simple little wind-up toy, right? I mean a complex, heavy-duty machine. As it boots up and those microcontrollers hum to life, it instantly has a massive workload. It's got to track its current speed. It needs to monitor its battery voltage so it doesn't just, suddenly die on you. It's pulling in continuous sensor readings, checking the ambient temperature, constantly updating its motor direction. It's a lot. But here's the fundamental question. Where exactly does the robot actually remember all this stuff? Well, the entire underlying architecture relies completely on how we handle variables.
Okay, let's dive into this. If you look at an amnesiac system, basically one completely without memory state, it literally can't track a sensor value from 1 millisecond to the next. That renders it completely incapable of doing calculations or making decisions. But when we introduce variables, boom, we create a functional bridge. We can capture a physical reading from a sensor, store it safely, process it through our logic, and trigger an intelligent action. Variables are absolutely crucial. They're the fundamental bridge between physical hardware and intelligent action.
Section 1. Inside the RAM warehouse. Formally speaking, a variable is just a named location in memory that stores information. But to make this visually attractive and easy to picture, let's imagine the microcontroller's RAM as this massive physical warehouse. In this setup, every single variable you create gets its very own physical, labeled storage box right there on a shelf, and it's designed to hold your data safely until the system actually needs it.
Now, check out the anatomy of a single memory box here. It beautifully maps what we humans can read to the physical hardware itself. So we assign a logical name, like temperature, and a value, like 32. But the compiler, it translates our human label into the exact physical hex address where that box sits in the hardware, something like 0x2000-2000-000.
Moving on to sizes and shapes. And this brilliantly illustrates exactly how the compiler acts as our warehouse manager. When your program boots up, RAM is allocated precisely based on data types. For instance, a char gets a tiny 1-byte box. A short gets 2 bytes. And a larger counter, like an int, well, that requires a 4-byte footprint. It's this highly optimized storage facility where every single data type occupies its own specifically sized footprint.
Next up, box rules, initialization, and scope.
Okay, so simply declaring int temp builds a 4-byte box, right? But it leaves it completely empty. And because microcontrollers recycle memory, opening an uninitialized box hits the system with random garbage values left over from literally whatever used that RAM last. It's pure chaos. Proper initialization, like setting int temp equals 25, ensures the box is immediately cleaned out and packed with a reliable starting value. Guys, proper initialization is absolutely critical to a stable embedded system. Don't skip it.
And that brings us to scope and lifetime. Local variables are pretty fleeting. They're dynamically allocated the second a function opens, and the exact millisecond that function ends, poof, the memory's freed up. Global variables, on the other hand, are permanent residents. They claim their spot in the warehouse right at boot up, and they stay there forever, globally accessible by any part of the program at any time.
All right, let's see these variables in action.
Here is exactly how this flows through a physical device. First, a real-world temperature sensor generates a tiny analog voltage. Second, the analog-to-digital converter steps in, translating that raw voltage into a digital footprint. Third, that digital number is routed safely into our pre-sized, initialized variable sitting right there in RAM. And finally, the main program reads that variable and pushes it out to an LCD display. The variable is basically the essential resting stop that allows the raw hardware to actually talk to the screen.
Now for the tricky part, warehouse hazards.
So here are the most common hazards that will absolutely crash your microcontroller. Uninitialized variables. Like we said, they inject pure chaos. Using the wrong data type, like say shoving a massive decimal into a tiny 1-byte char, that causes instant data corruption. Overflowing a variable literally wraps the number all the way back to 0, totally breaking your math. And finally, relying entirely on global variables for everything will just quickly exhaust your RAM and create unmanageable spaghetti code. Keeping variables local whenever possible is for sure the key here.
Which brings us to our final thought for this explainer. We've successfully set up our RAM warehouse. Variables have given our robot the power to perfectly remember a temperature reading, which is awesome. But a robot that checks the temperature once and then just goes to sleep isn't very useful, is it?
So how do we force our code to check that variable, process it, and update the display 1,000 times every single second without writing 1,000 lines of code? Well, keep that question in mind, because that is exactly what we are going to master in our next deep dive into loops. Thank you so much for hanging out and learning with me today, and I'll see you in the next explainer.